Welcome to another video explaining the universe using the particle. Well, my name is Bob D. Hilster, and I am your particle model. I'm presenting today a video on superconductivity, part 3, and it's about levitation and suspension using superconducting material. A viewer had asked a question a while back. The viewer's name is 635574, and he asked these questions, and I've talked about the items here in blue, and now I'm going to talk about magnetic levitation and suspension. This is a video that I'm going to use to talk about this effect, and it's titled How Superconducting Levitation Works, and you can watch this video. It's well done. It's kind of a demonstration, not really a technical explanation in any detail, but they do discuss the Meissner effect, magnetic levitation and suspension, and the flux trapping effect. Now, the video starts just by explaining what's there. There's a small disk here. It's a yttrium, barium, copper, oxygen superconductor that they made themselves, sitting in what looks like a styrofoam plate. There's an iron spoon and a magnet. And it goes through a couple of demonstrations, bringing the iron spoon to the superconductor. Nothing happens. It doesn't stick. And then he brings a magnet, sets it down, and removes it. It doesn't stick. And then finally he puts it there, the magnet, on the superconductor. And when he brings the iron spoon close, it jumps up and sticks to the iron spoon. Superconductor does not jump up and stick. If you remember any magnetic tricks you did, you bring a magnet, a normal magnet, to a paper clip, and when you get close, it jumps up and sticks. This is one of the important points here, because in this case, that doesn't happen. And it's called the Meissner effect. So they they add liquid helium, which has a cooling temperature of 77 Kelvin. The superconductor has a temperature coefficient of critical temperature of 91 Kelvin, I believe. And they add this, and they wait for it to be cooled down to 77 Kelvin. Then he takes the magnet and he moves it towards the superconductor, and it repels. It doesn't jump up and stick like a paper clip would to a normal magnet. But it repels, meaning it's probably magnetic, but it's moving away rather than being attracted. And they use the Meissner effect to try to explain why it's repelling. And he moves this around, and he does it in 3 different directions, and it repels each time. Well, the Meissner effect, you can look it up in Wikipedia, and it's explained this way, is the Meissner effect is the expulsion of a magnetic field from a superconductor during its transition to the superconducting state. Well, it happens during the transition, apparently, but when it's supercooled, the magnetic fields are expelled or removed from that's what they say happens, okay? But they don't have direct evidence of this. They detected this effect only indirectly, because magnetic flux is conserved by a superconductor. When the interior field decreases, the exterior field increases. I think they stated this wrong. I think if they can detect anything, they detect a field increase outside, and hence conclude that there must be a decrease inside, because they can't see inside, but they can measure the field outside. That's the Meissner effect. They claim this effect happens. And this is a diagram of how that the arrows represent the magnetic flux lines at room temperature, or the temperature is greater than the critical temperature. The flux lines go straight through. But when you supercool it, the temperature is less than the critical temperature. They all go around. I'm always one looking at what they really have done here. Well, ironically, there's 9 flux lines here and only 8 here. Why they excluded the 9th one here, I don't know. It bugs me a little bit that they didn't do the drawings the same way. Well, there is a demonstration, an experiment, if you will, that they've done, and you can get this from Wikipedia. Look up Meissner Effect, and you'll find these pictures. And this instrument has an electromagnet with a north pole and a south pole, such that when they turn the electromagnet on, there is a field lines going from north to the south, that is from left to right. In the middle is a jar called a Dewar jar, and there's a panel, a kind of a plate with the superconductor mounted on it, and there's compass needles here. You can't see it. And there's a meter here indicating the strength of the magnetic field that they're using during the test. Okay, so this is the result. These compass needles are placed, they're pinned down in these locations, and at room temperature with no liquid helium in the jar, the needles line up this way. And it looks like it takes, there's 8 lines here and 8 lines over here. And it looks like this line goes through here, and this line comes down and goes through, and same thing down here. They don't show the middle one. Why? There's room to put a needle here and here. I don't know why they don't put it there. But then when they pour the liquid helium in the Dewar jar, then these needles change position. And not all of them cleanly look like they go through. I'm a little bit suspicious why they pinned these needles the same way. I think these positions are there to match this flow. Okay, it doesn't match this flow very well. If you follow this line, this one's not pointing to that one, this one's not pointing to that one. Whereas here, yeah, okay, I get it. The field lines are going that way. That's what we would normally say. But over here, it's not clear where the field lines are going. And again, I point out, why didn't they put 2 compass needles here and 2 here so we could see that? They don't have it. Well, what about the particle? What does the particle model say about this? Well, these compass needles, if you listen to anything that I've done on the magnetic fields, these needles are controlled by equal G2 forces on the needle. In other words, if this needle is going to have that position, this net force and this net force have to be equal across the needle, all the way across the needle. So the position of this needle is controlled by the G2 forces. So if you look at room temperature, almost all of these needles in a very, mostly, not exactly, the forces are straight up and down, like this superconductor wasn't even there. It has no effect. In other words, the forces here on this needle are pointing in this direction. The forces on this needle are pointing down in this direction. They're generally vertical, straight vertical forces. Over here it's different. Look where this one's pointing. The G2 forces pushing this thing, getting it into that position, is pushing it that way. Same way over here in this one. You can't see it as clear because this photograph is at an angle, but it tends to look like it's vertical here, but as you get closer, it starts bending towards that way. When you get here, it's really bending. And here, it's back to straight up and down again, which you would expect. What this tells me, and I don't know why this is true, or is that when it's supercooled and you have more open space, then you can have more flux lines flowing through here than they're showing. There's 8, here there's 8, but I contend that more flux lines get through, therefore there's more G1 particles in here setting up a stronger force in this direction. That's why these needles go here, not because of expulsion. All right, the particle model, the magnetic field is made from high-intensity streams of G1 particles flowing. That's what I was talking about. And these particles pass easily through a normal conductor. They will also pass easily through a supercooled conductor, even more easily than through a room temperature superconductor. Further, it is well known that a superconducting magnet has a stronger magnetic field than a regular electromagnetic when it's not cooled. So yeah, you're expecting a stronger field around this, and that's because the superconductor allows more G1 particles to flow through. The G2 force field becomes stronger, and it traps more and more of the G1 particles, making that that strong magnetic field. Well, let's talk generally about magnetic attraction and repulsion in my terms. The G2 pushing force surrounds each one of these in all directions. And that pushing force is what causes attraction. And it's around this one when when they're attracting. I got north and south. This is attraction. This is north to north, and this is repulsion. But G2 pushing force around these is the same. Even when it's being repelled, the reason it's repelled is because this repelling force right here is stronger than the G2 force around it. Pushes them away, even in the presence of that. In this case, these are lined up, moving the same way. They don't do anything. They just flow right through from the north to the south and out and around. They don't do anything. There is repulsion up here a little bit. There's a little bit of repulsion in this area. So you have a very small repulsion and a strong pushing force pushing them together. G2 pushes them together. Collisions of G1s cause repulsion. And it's a matter of which one is stronger. And what I'm saying is they both happen. They're always there, both of them. It's the same with Newtonian gravity. I'm sitting here, and there's forces pushing me up through the earth just as much as there's pushing me down. There's more pushing me down. They're there. They're both there. We talk about a net force, but that doesn't mean that the other ones that balance out aren't there. They're still pushing me up, pushing me down equally. The extra ones pushing me down are is the net force of gravity. They're both there at the same time. Okay, what they claim, however, is that this superconductor has a characteristic of being diamagnetic. Somehow, he's gone through this process, the magnetic field here is opposite to the magnetic field here. How that happens when you can assume the magnetic field, and I did this later in the drawing, that it's going up and around and down. And why would it cause this to go down, around, and up? Because there's this source. The source of this magnetic field comes from this one, and somehow this decides to go the opposite direction. All they say is it's diamagnetic rather than paramagnetic. You can put a name to it that doesn't explain what's happening. Well, here's my analysis. When this is floating in liquid helium, and you bring this magnet, which has a magnetic flow up, around, and through, up, around, and through, I claim that it will create the same flow here. The same flow, because that's the direction it's going here. That's the direction it's going to go here. Except this is a superconductor. When it's supercooled, the atoms in this arranged such that it allows more G1 particles to flow through. That's why the heavier red lines. This is a stronger field than this field. Well, as you bring this magnet towards the superconductor here, right here you have opposing G1 particle flow. You have high intensity stream here. You have an even higher intensity stream of G1s here, hitting each other, pushing it away. Actually, this is pushing that away, but because this is floating, this is being held by his hand, this is floating, this moves away, but it's because this stronger force is pushing them against the magnet. There's another interesting possibility. If there are, in fact, more G1 particles here and some of these hit here, you have more G1 particles hitting this than normal. These could be pushing against the magnet. Interesting possibility. Do I know that's happening? Do I even know that this is really the E answer? No, but it is one possible answer that the particle model suggests. That doesn't require this to be diamagnetic. Well, levitation. What the viewer does, the demonstrator does, is he takes the magnet and he holds it very close with a strong force because he's fighting the repulsion, and he holds it there for a long time, sort of trying to get this thing to be stable. It doesn't. Apparently, you can't just put it there and it works. You got to hold it there. You watch it. He has to. He stays there. A long time. In terms of magnets, usually you put them together, they're instantly repelling or attracting. This he holds, and he holds it long enough that it stays in place when he removes his hand. He claims this is the flux trapping effect, and what it shows is that in this case there are magnetic field lines going through the superconductor. And how does that happen? Well, their explanation is that if you have a superconductor that's very thin, a type 1 that's thin or a type 2, they will do this. And they're saying that these flux lines will find points in the superconductor that allows for these vortex things to come together, and they call these vortexes here, and this pins the magnet in its place. Actually, this is the superconductor this time, and the magnet is down here. And they claim it's this flux trapping effect that holds it in place. Well, this is the particle model levitation, and it's also for suspension. If you flip this upside down, this says the same thing. So what I have here is I have a superconductor here, a magnet here, and their relative forces, and you have repulsion here, and possibly repulsion here. You have enough repulsive force to balance out the attraction G2 pushing force, that they reach a unique balance. Now keep in mind they've made this thing exactly the size it needs to be, that for example, for suspension, this won't fall down. Gravity won't push it down too far and have it fall apart. So this what this piece of material is, what its size is, and what the size of the magnet is, and the size of its magnetic field is all kind of tuned to make this work. You change this to a different material, it doesn't work. You change it to a different size, it won't work the same. This is, I don't want to say a gimmick, but it's set up to do this, and it does. It works, and the particle model claims that you have both repulsion and attraction in any of these gravity-type situations. And if the balance is right, you have just enough magnetic field here and just enough magnetic field here, this situation occurs. That's the particle model explanation for levitation and suspension, because if you flip it over, it's the same picture. Doesn't change. My name is Bob D. Hilster, and I am your particle guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.